briefly introduce Antoine. So Antoine, is now senior quant at Danske Bank. He has had several positions in the industry, including global head of the quant research at BNP Paribas. He has worked a lot on automatic differentiation, and is precisely showing how this AAD can be applied to neural networks to improve the learning using neural networks combined with AAD. So, George, if you're ready to transmit.
Hello, everyone. This is Antoine Savine from Superfly Analytics at Danske Bank, and I'm here with Brian Hughes to present our latest research on pricing with machine learning and automatic differentiation. Closed-form pricing a la Black-Scholes is only available for simple products in simple models. With more realistic models and more realistic transactions, prices cannot be computed in closed form, and numerical methods like Monte Carlo are necessary. This is too slow for many practical applications, including the risk management of large option books, the computation of exotic risk reports in multiple scenarios, backtesting, value at risk, and all regulations where trading books are repeatedly evaluated in different market scenarios. This is why we need approximations capable of quickly computing approximate prices as functions of the market state. In stochastic volatility models like SEBR, for example, there exists no closed-form formula for European calls. Famously, Pat Hagan cracked an accurate approximation 20 years ago, effectively bringing stochastic volatility to trading desks. Today, we want to generalize and automate the production of pricing approximations for arbitrary transactions with arbitrary models. We want to learn pricing functions online in real time with convergence guarantees. We achieve this by combining machine learning with automatic differentiation, or AAD, in our working paper, Differential Machine Learning, available on ArXiv. We work with arbitrary models specified by the dynamics of a state vector. The state vector represents the current state of a market. In Black-Scholes, for example, the state is the spot price of the underlying asset, and its dynamics is a geometric Brownian motion. A stochastic volatility model like SEBR specifies a joint dynamics for the spot price and its volatility, so we have a two-dimensional state. In a labor market interest rate model, we have a high-dimensional state containing the current values of all forward LIBORs on the yield curve. In general, we deal with high-dimensional states collecting all the market variables affecting a transaction or a trading book. The model specifies the dynamics which allows to simulate paths for the state vector together with necessary path dependencies with Monte Carlo. We also work with arbitrary transactions or trading books defined as collections of event-driven cash flows. The cash flows are specified as functionals of the path of the market state variables. The payoff of a transaction is the sum of its cash flows. For example, a European call pays ST minus K plus, where ST is the final spot price. A barrier option dies if the spot price hits the barrier at any time before expiry. More generally, derivative systems specify transactions with some way of describing their cash flows as functionals of the path of the market variables. Modern systems often include domain-specific scripting languages for the description of cash flows. For example, this is a worst of 4 autocallable transaction described in Danske Bank's proprietary scripting language. Given the specification of its cash flows, we can compute the payoff of a transaction as a function of the path. The price of a transaction is the expected payoff under the martingale measure specified by the model. and it is generally estimated as the average payoff across the paths simulated by Monte Carlo. Although we can always compute the price by Monte Carlo, our goal is to learn a much faster computation. In order to learn the pricing function, we produce a training set with Monte Carlo simulations. We simulate a training set a la Longstaff-Schwartz, where training inputs are initial states, denoted xi, and training labels are final payoffs, denoted yi. Importantly, our training labels are not prices, which are conditional expectations computed numerically for a massive computation cost. In order to train on prices, every training example must be computed by Monte Carlo. By contrast, we train on payoffs, so every training example is computed with only one path. The whole training set of m examples is computed with m paths, for a cost similar to one pricing by Monte Carlo. Therefore, datasets of payoffs are suitable for training approximations online, in real time, contrarily to datasets of prices.
The next step is to train the machine on the dataset of sampled payoffs and watch it converge to the correct pricing function. You can reproduce this result with our TensorFlow implementation notebook on GitHub. We have a mathematical guarantee that a universal approximator like a neural network trained by minimization of the mean squared error between the simulated labels and the predictions of the network converges to the correct pricing function, which is the expectation of the final payoff conditional to the initial state. Convergence is realized asymptotically when the capacity of the approximator grows to infinity and the size of the training set also grows to infinity. Proof is given in Appendix 1 on GitHub, the intuition being that the true price is the expectation of the payoff. Hence, payoffs are unbiased estimates of prices with the addition of independent noise, diversified away in an asymptotically large dataset. The key argument is that the payoff is an unbiased, if noisy, estimate of the true price. This is what authorizes to train machine learning models on simulated payoffs with guaranteed convergence to the correct pricing function. Of course, this is an asymptotic result. With a finite dataset, the noise is not fully diversified and training remains vulnerable to overfitting, a phenomenon known as variance in machine learning literature. We are going to present a very effective regularization which mitigates overfitting and reduces variance, allowing to reliably train on small datasets computed in reasonable time. The result is also somewhat theoretical. It is the global minimum of the mean squared error that converges to the correct pricing function. But there's no guarantee that your optimization algorithm finds it in finite time. It turns out that we can do something about this too. In Appendix 4, we develop a special network architecture with worst-case training guarantees. The convergence result is valid with all types of universal approximators, including neural networks, but also classic regression and most other types of machine learning models. We work with neural networks because they offer automatic feature extraction. Neural networks perform a linear regression on a set of features which they extract from data by themselves and encode in their hidden connection weights. As a result, they learn from simulated data alone. There's no need to manually specify meaningful regression features from prior knowledge of the transaction and the model, as is customary with implementations of the Longstaff-Schwartz algorithm with linear regression. Because they work with simulated data without prior knowledge of models or transactions, neural networks are suitable for very general machinery applicable to a wide variety of transactions and models. Neural networks are also optimized for computation on modern hardware. They are capable of predicting values by feed-forward induction and sensitivities by backpropagation, very efficiently with practically analytic speed. This being said, our differential approach easily carries over to different types of machine learning models. As a first example, we consider a 30-stock basket option in a 30-dimensional correlated Bachelet model. This example is implemented in our demonstration TensorFlow notebook on GitHub and easily reproducible. The charts measure the performance of neural networks on independently simulated test data. The cyan dots are the predictions of neural networks trained on datasets of increasing size, compared to the correct prices in red as a function of the initial basket on the horizontal axis. The correct price is given by Bachelet's formula, applied with the initial basket and its volatility. Neural networks make predictions based on the 30-dimensional state. It is clearly seen that predictions converge towards the correct pricing function as promised by the convergence result. But it takes hundreds of thousands of examples to achieve an accurate approximation. With smaller data sets of 8,000 to 32,000 examples, the approximation errors remain unacceptably large. Predicted deltas follow the exact same pattern but converges a lot slower. With smaller data sets, the network essentially predicts random deltas. Deltas are related to the shape of the pricing function, and the network struggles to learn the correct shape from punctual examples.
Predicted prices and deltas converge, but prices converge too slowly for a practical application. Hundreds of thousands of training examples cannot be simulated in reasonable time. Convergence of deltas is even slower. To resolve these problems, we took inspiration from the field of computer vision, where data augmentation takes one labeled picture and makes many of them by cropping, zooming, rotation, recolor, effectively increasing the dataset for zero cost and reducing variance without introducing a bias. Data augmentation also teaches the machine important invariances, and we took similar steps with differential labels. What we will do is use the differentials of training labels with respect to the training inputs to explicitly teach the machine the shape of a pricing function and improve performance on small datasets. We minimize a composite cost function which combines the classic MAC between value labels and value predictions with the MAC between differential labels and differential predictions. Differential predictions are the sensitivities of the value predictions with respect to inputs, that is, the risk sensitivities, as predicted by the machine learning model. In a neural network, these sensitivities are computed very efficiently with classic backpropagation. In general, backpropagation computes the gradient of a cost function with respect to the connection weights for optimization. Here, we use backpropagation to compute the differentials of the output, the value prediction, with respect to the input state variables. So we effectively predict risk sensitivities by backpropagation. First, we feed the initial state into the input layer and execute the sequence of feed-forward equations to compute a value prediction. Then, we execute the backpropagation equations in the reverse order to compute the sensitivities of the value prediction in the output layer with respect to the state variables in the input layer. We can combine value and risk predictions with a so-called twin network. Its first half is the original network, traversed with feed-forward induction to predict a value. The second half is traversed with the backprop equations to predict risk sensitivities. It is the mirror image of the original network with shared connection weights. Like feed-forward induction, backprop applies a sequence of matrix by vector products activated with a differential of the activation in the original network. The twin network predicts prices and computes their sensitivities to the input state variables, aka the risk sensitivities, in just one combined computation for twice the cost of price prediction alone even when we compute hundreds of thousands of sensitivities to that many state variables. Recall that we want to train by minimization of the errors of differential predictions compared to differential labels. What are these differential labels? Well, there are the sensitivities of training labels with respect to training inputs, that is, the sensitivities of the final payoffs with respect to the initial states, also called pathwise differentials. Pathwise differentials are computed in the simulation engine and fed into the training set. For example, in Black-Scholes, the final payoff is st2 minus k plus, and the initial state is st1. The pathwise differential is dst2 minus k plus dst1, and we compute it with an application of a chain rule. This is dst2 minus k plus dst2 times dst2 dst1. These two terms are easy to compute, and we get a concise formula. This is the indicator of a spot terminates in the money times the log return. Notice I can compute the pathwise differential very efficiently together with a payoff along a given path without having to regenerate the path. The pathwise differential is also a random variable dependent on st2. We can compute its expectation with elementary calculus, and the result is n of d1, the Black-Scholes is delta. These two key properties carry over to arbitrary models and arbitrary payoffs, provided appropriate smoothing. First, the pathwise differentials can always be computed with an application of a chain rule to analytic accuracy and very efficiently together with a payoff for very little additional cost. And we don't need to compute it by hand for every combination of transaction and model like we just did in Black-Scholes. Automatic adjoint differentiation, or AAD, is an algorithm capable of performing this computation automatically behind the scenes by a systematic application of a chain rule, and with guaranteed efficiency of constant time regardless of the number of differentials. AAD is now widely considered one of the major algorithms in quantitative finance. Its applications include instantaneous calibration, real-time risk reports, and many others. In the context of this talk, we use AAD to efficiently compute the pathways differentials we need as differential labels for training pricing approximations. If you are not familiar with AAD, you can learn all about it in a vast amount of articles, including the founding Smoking Adjoints by Giles and Glasserman, as well as a variety of textbooks and even movie tutorials. The second key general property of pathways differentials is that true risk sensitivities are expectations of pathways differentials because expectation and differentiation operators commute. Hence, the differentials of the expectation are the expectations of the differentials. This is assuming appropriate smoothing, which is standard practice in capital markets. Importantly, this means that pathways differentials are unbiased estimates of true risks, just like payoffs are unbiased estimates of true prices. By the same argument we have seen for payoffs, this means that pathways differentials qualify as training labels. We are authorized to train approximators by minimization of the MAC between predicted sensitivities and pathways differentials with guaranteed convergence towards a pricing function with correct risk sensitivities.
Training with differentials provide a very powerful regularization. Compare with classic Tikhonov regularization, which penalizes large weights. Differential training penalizes incorrect differentials. Like Tikhonov, it prevents overfitting and reduces variance by introduction of a penalty. Unlike Tikhonov and other classic forms of regularization, it doesn't introduce a bias and is virtually insensitive to regularization strength. With differential training, there is no more bias variance trade-off. Recall that differential labels are unbiased estimates of true sensitivities. Hence, training on differentials alone converges to an approximation with all the correct sensitivities. That is, the correct function, modulo, and additive constant. The penalty for wrong differentials doesn't deviate training from converting to the correct pricing function. It just reduces variance in a similar way to data augmentation in computer vision. Differential machine learning also augments the training set with differentials and allows machine learning models to learn the correct shape of the functions they want to approximate. It is also a form of data augmentation. We measure practical performance on the 30 stock basket option from the TensorFlow notebook on GitHub. The charts on the left display the predictions of conventional neural networks trained on datasets of increasing size as previously. The charts on the right display the predictions of the twin network trained with differential labels. What we see is a stellar improvement. We get an accurate approximation of the pricing function with datasets as small as 8,000 samples, and increasing the dataset to 16,000 and 32,000 samples, we achieve a virtually perfect approximation. We have a similar improvement for the prediction of deltas. Differential machine learning effectively prevents overfitting and authorizes to confidently train approximators on small datasets, simulated in realistic time, and reliably apply them for the computation of prices and risk sensitivities. You can reproduce these results easily with our demonstration notebook. We made it publicly available on our GitHub repo, Differential Machine Learning. It is designed to run on Google Colab online, so you can execute it in your browser on Google's GPU servers without a local installation of TensorFlow. The notebook implements conventional and differential machine learning on TensorFlow and discusses many practical implementation details, including data preparation, network architecture, weight initialization, optimization, and more. The machinery is general in terms of transaction and model, and seamlessly carries over to real-world situation. As a first realistic example, consider a worst of 4 autocallable transaction with 4 correlated local volatility models a la de Pierre, calibrated on current market data. We trained a conventional neural network on 32,000 examples simulated in Superfly, Danske Bank's proprietary risk management system, and measured performance of price approximation on the left and delta approximation on the right on an independent test set. The test examples are displayed as cyan dots with correct prices on the horizontal axis, computed with nested simulations, and the predictions of the trained network on the vertical axis. Perfect predictions will line up on the 45-degree line in red. We see that the network learned an accurate pricing approximation, but the predicted deltas is essentially random. By contrast, a differential network trained on only 8,000 examples learns a virtually perfect pricing approximation, along with a very decent approximation of the Greeks. The predictions of the differential network are displayed in purple. Finally, we can apply the machinery to entire netting sets or trading books. In the last example, we learned the pricing function of one of Danske Bank's netting sets, simulated in our proprietary XVA model as a function of a 20-dimensional state vector. We trained the neural networks on 8,000 simulated examples. As before, we monitor performance on an independent test set by comparison with correct prices produced overnight with nested simulations. The conventional neural network starts converging to a correct approximation until performance stops improving mid-training when overfitting kicks in, resulting in a very poor approximation. It took 65,000 examples and some hyperparameter tweaking to learn a decent approximation with a conventional neural network. By contrast, the differential network easily learned an accurate approximation from only 8,000 examples with the default hyperparameters. Differential labels computed with AAD for very little additional cost effectively regularized optimization and prevented overfitting. Notice the inaccuracy on the right asymptotic. It disappears with 16,000 examples, but we wanted to show you the problem. Machine learning models typically struggle to learn a correct asymptotic behavior because we have little data from extreme scenarios. Specialized algorithms are needed to correct the asymptotic behavior of learned approximations, and they are discussed in detail in our Appendix 4 on GitHub. There we also use differentials in order to find the correct extrapolation. The complete presentation is available on deepanalytics.org. The working paper is on arcsit.org, and our GitHub repo, Differential Machine Learning, contains the demonstration notebooks and the appendices, where you can read about mathematical proofs, practical implementation details, and multiple extensions. On behalf of Superfly Analytics of Danske Bank, thank you everyone for your attention.
Before we leave, I would like to take 5 minutes to make a live demo, show you how all the material we have seen is implemented in practice. I will make the demo in Danske Bank's production systems. This is a new development for us, and its implementation is experimental for now, but we can still give you a good idea of how everything fits together in a practical risk calculation engine. The training set is computed with our front office pricing and risk management system with the same model and the same parameters that we use for live pricing. The system is coded in C++ and runs on parallel CPU. When the training set is ready, including the pathways differentials, the system communicates it to the training platform developed on TensorFlow and running on GPU. The platform trains the neural network, which means that it finds the connection weights that minimize the combined MEC, as we have seen in the presentation. After training is complete, it communicates the trained connection weights back to the front office system. The weights encode the pricing function, so the risk system can now predict prices and risks as functions of states by induction through the twin network. Armed with a learned pricing and risk function, the system can easily compute exposures, quantiles, and all kinds of risk aggregates. So this is Superfly, Danske Bank's proprietary pricing and risk management system. I'm piloting Superfly from Excel, but the action takes place on the quant server in the upper right corner. In the lower right corner, you see the TensorFlow trainer listening for training requests. First, I create a transaction by scripting its cash flows. This is a worst of 4 autocallable bond. If you are not familiar with cash flow scripting, think of it as a translation of a term sheet into a language that the system understands and interprets. I also explicitly smoothed the various barriers involved in the autocallable so that Superfly can safely differentiate the cash flows with AAD. Next, I load an appropriate model for the transaction. In this case, a set of local volatility models à la Dupire correlated with our official correlation metrics. The model is configured for live pricing and calibrated to current market data. I have everything I need now to price the transaction. You can see that the autocallable bond is worth around 96 today. I could also compute its AAD risk report, but I will skip that today. Instead, I'm going to decorate the script to learn a pricing function for the autocallable bond in 6 months on December 20. I am instructing the system to learn the pricing function of the autocall on that date, which authorizes me to use the learned approximation in the script to make arbitrary risk computations. Here, I'm simply storing the pathwise value predictions in the variable PV6M. Now, I enable training and recompute the value. What this does is instruct the system to compute a training set complete with pathways differentials. Watch the TensorFlow listener in the lower right corner. When I fire the computation, it will pick up the training set and train the neural network. Doing it now. Superfly generates the training set and wakes up TensorFlow. TensorFlow trains the neural network and displays the learning curve for our reference. Then it communicates the trained weights back to Superfly. Armed with an encoding of a pricing function, the system simulates market scenarios and computes the future value of the bond in those scenarios. In this case, I have 8,000 market scenarios produced in the pricing model for simplicity, but it doesn't have to be the case. The market scenarios could be generated in arbitrary models, including ones calibrated to historical data. The system now computed the future value of the autocallable bond in the 8,000 market scenarios by evaluation of a trained neural network. I can pull these 8,000 values from memory, along with the final payoffs on the same 8,000 market paths. With these numbers, I can easily compute an exposure, a quantile, or an arbitrary risk aggregate. Here, I just display the distribution of a future value in red, along with the distribution of final payoffs in blue. Actually, I could script an arbitrary risk computation along with the cash flows of a transaction, including XVA, CCR, FRTB, or CMMVA. We have seen how we can learn and use a pricing function on one given exposure date. The machinery is easily extended to multiple exposure dates and for a limited additional cost. But this is a story for another day.
Okay, thank you very much, Antoine and Brian, actually, who was also featured in the video. Antoine and Brian, actually, who was also featured in the. So, are there any questions from the audience? Please, in that case, use the YouTube chat. I will maybe start with a short comment. I think I already made you. It's actually you, Antoine. You even actually don't need the smoothing somehow. So you even payoffs that are not smooth will actually work in your setting. The only thing you need is that the pathwise derivative. I mean, that the derivative can take the form of the expectation of some random variable h, which, I mean, for instance, Magellan calculus is a good tool to generate those random variable h, and that's actually precisely one of the things that was done in this Warin paper of 2018. So actually, it's even, I think, like the applicability of your method is even more general in that sense, that as soon as you are able on each path to generate an hi, so that's the expectation of the h is actually the for instance, the delta or the Greek that you need, then your method will work. I'm checking on the YouTube. Yeah, so George has a question. Can you say a couple of words about how to collect the needed data to train the network? How much is it dependent on the available data?
I actually don't collect any data, right? I simulate the data. We work with simulated data. So it's I can simulate as much data as I want, or depending on my computational budget, of course. Remember does it work, by the way? Am I streaming? Because
Yeah. We can hear you, Antoine.
Okay. Now, I was saying that here we are using machine learning as a numerical technique, if you wish, in the sense that we are trying to learn, as I tried to say first in the beginning of the video. What we are trying to do is collecting data from Monte Carlo simulations, collecting pathways data, in order to learn on the fly pricing approximation, just like SEBR is a pricing approximation, except we do it by machine learning techniques here. So the data that I'm collecting to train the neural network is simulated by Monte Carlo. So I'm trying to learn the price of some arbitrary transaction in some arbitrary model, and what I need is some collection of paths simulated in this model for this transaction, and this is my data. Yeah.
Thank you, Antoine. Any other question? I don't see on the chat. Okay, well, given that it's past 9 of any hour that's your local hour, I think we are done for the day. Thank you to all the speakers, not only of this session, so Beatrice and Antoine, but also everybody who gave a talk today. We are due to reconvening tomorrow, so at your different local times, 12 noon in Rio, 10 a.m. in New York City, and you make the translation for your local time. So thank you very much for joining, and see you tomorrow for the third day of the conference.
And thank you so much, Julian, for being there, and for Antoine and Beatrice for the fantastic talks you gave, and to everyone who participated. So see you tomorrow, as Julian just said. Bye.
See you tomorrow.
See
Bye.
you. Have a good night, George.
As a matter of fact, for me it's today, but
Yeah.
anyway.
I know.
Bye.
Bye-bye.